put this thing, right? So you can take the supremum of this, where x you are taking from the sphere, from the unit sphere, right? This is 1. And you take supremum of these quantities. All right? These two definitions are same. Intuitively, what is happening is you are taking first, if you look at the right hand side, which is why I defined it last time, right? You take all possible things with length 1, right? With length 1, that's all we are doing, nothing else. So take all possible things with length 1 and compute their AX, compute the output, come see where the matrix takes, right? So I mean, just a very simple picture will that be, you just take the unit circle in two-dimensional case, you take the unit circle and see what the matrix does to it. Maybe it will send, maybe I just take some colors, right? Maybe it will send this thing to this thing, who knows, right? And it may send this thing to this thing, right? And of course that decides everything, but still for writing we don't really know, so we just say maybe it sends this thing to this thing, right? So you have to collect all these things. I mean, you can draw these things on your own and think about these things. You collect all these blue.
Non-x.
Norm x equal to 1. That is right.
How it looks like.
Yes, exactly. Yeah. So norm x equal to 1, in the picture how it looks like, it's simply, so what is this? This is basically all the vectors for which the sum of the two coordinates is equal to 1. You agree?
Okay.
Right? And this is the good old unit square, a unit circle. High school coordinate geometry, everything, right? You know this.
Yeah, got it.
Absolutely, right? And then just basically you spread the vectors on the unit circle and you take their output, where the matrix takes it. Okay? And these outputs you collect and take their supremum of their norms. That is the.
But every output will be bounded in the circle. Then
no.
all
output,
the vectors will.
Output may go outside the circle, right?
Okay.
You don't know. Do you know?
It's just changing the direction.
Direction? No. Why? Length can also change, right? Right? Length can also change. So yeah. Obviously, those matrices which don't change the length, they are useful. They are called unitary matrices, orthogonal matrices, which very important. But right now we are not talking about them. So, anyways, this is the definition, and similarly, this is the other definition. Yeah, let me not say those things right now. You think about why these two things are same. Just think about it. This is not a homework. Okay, this is not homework. Just think about it. It's not difficult, but yeah. What I wanted to do is to show. So yeah, first thing is that, let me write the main thing is that this is the, or maybe like this, because this is left hand side is known. It is the right hand side which we are trying to define, right? This thing. This is norm of A. This is the definition of norm of A. The key fact, the very key fact which was useful in our problem last time, it's also just a theorem, it's a property, is to show, and it's very easy actually, is to show that this is less than this. Correct? This is what we wanted to show, right? This is the all important inequality. It's similar in resemblance to this one. It's just multiplicative. Submultiplicative is subadditive. It is submultiplicative, not multiplicative, but submultiplicative. So how do you show it? How do you show it? How do you show this? So, right. So you want to say that the norm of this thing is less than the norm of this times the norm of this, using this definition. This definition, maybe for you it will be a little uncomfortable to work with, but soon it will be fine. So let's take it. So yeah. So let's take AB and take any x. Take any x. Okay. Take any x and consider this norm. All right. This thing you know that this thing is, now you can consider it like this. You can think that bx is the input and to the matrix A, right? You have to interpret these things,
Okay.
right? Then this thing you know is less than norm of A times norm of
Norm
bx.
of px.
Bx is the vector, right? Here it's being replaced. This, you see, this is the same thing as ax is less than or equal to norm A times x, norm x, right? Yeah, or maybe I should. I mean, if you look at the second definition, it is obvious, but I should say it properly. Uh, One, right? Yeah. So if I should say it properly, then I should say it properly. Yeah. I'll just use the first definition. Otherwise, it shouldn't look like some magic. It should not look like magic, right? So because you see, you can ask, right? I mean, in this definition, everything has norm one. So I should be telling you based on that only. For the time being, right? When you get comfortable, then it's different. So if I have to say it in that way, so let me make that effort and say it in that way. That is important. So uh, yeah, take this. Sorry.
You did the quotient by x by norm bx.
Yes, because this is a real number, right? Norm bx is a real number. Okay, right.
Yes.
Norm bx is a real number, so maybe I'll write it in a this way. See, so you want to look at this quantity, right? Because you want to
Mm-hmm.
apply the definition of A, one thing at a time, this quantity, and obviously you want to look at this quantity, but I will look at this quantity. Okay, I can divide. It's a non-negative number. Sorry, it's a, yeah. I mean, if it is zero, then something happens, but that I will leave for you to think. What happens if bx is zero? That's a trivial case. Okay, bx is zero, then left hand side
Okay.
then zero. So I'm just dividing by this, and then you see, this is your lambda, right? This is like a lambda. So you can take it inside the norm, right? Which you proved earlier. So you
Oh
can
yeah.
take it
Yes.
inside.
Yes.
Yeah, that's the sort of magical properties of norm, right? Or other good properties. And then E is the matrix, Bx is the input. So you can also take the scalar inside. Think of this like a scalar, like a lambda, right?
Mm-hmm.
Right. So it's nothing but it's just like a scalar. Okay. Now you know. Now you know that this thing has norm one. This thing has norm one, right? Correct. Because the
Yes.
vector v,
Yes. Yes.
you
Yes.
know that, right? Yeah, it's the typical norm one vector has norm one, and then you know that because it has norm one, uh, because it has norm one, this will be less than or equal to norm A
Okay.
by definition,
Mm.
because norm A is the supremum. This is a y. This is a y, right? Ay norm ay. This thing, think of it as a just a vector with norm one. Call that vector y. Then you take ay. What is norm of ay? It is less than norm a, because norm
Uh,
a by definition is the supremum of all those things.
yes. 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 Yes.
That's the thing.
We can take it.
Exactly. I understand that it may look like a little bit of a trick, but there is no trick involved. It looks like trick because the language is not properly laid down. But it's fine. You take it as trick for now, and gradually it will become. When you see the bigger picture,
And then take the
exactly.
px there.
Yeah, take the BXR and repeat the same process. Okay, and you'll be able to prove.
Mm.
You'll be able to get here. Okay, and obviously take x to be norm x equal to 1. Right. So I'll leave that. So this is the thing. It's the sub-multiplicative. You see, there are a lot of things you get comfortable with in this domain. So yeah, it's taking a bit of time, but it's okay. Right. Let me. Can you try number 5 again on your own? Maybe. As for small cases, try. I proved one side last time. Try the other side on your own. This is some calculation. I'm not getting it. Yeah. Yes. And this thing. So, did you figure out a pattern in this? P of, or maybe we'll do this next time, right? Leave it. Let's do it next
In the
time.
Pascal matrix.
Yeah, yeah. Do you see the pattern?
Yeah, I find out the pattern actually. The
Yes.
both matrices look same. The diagonally one will continue,
Right.
and then we have to swap plus or minus accordingly.
Yes, right. So you can figure out what the thing is, right? So maybe it's just that it is just the inverse n cross n. It is just I choose j, right?
Hmm.
Wait, yeah. Okay, it is this I choose j. Now, how to prove this pattern? You have to think that will come down to some again some binomial identity and thing like that.
What is this?
Some binomial identity. Why will it come down to that? So let us write here. Let's write it. So you see, you are saying that there is this matrix. This matrix, and again there are again better ways to say those things, but we will not be able to say it now. Some theory comes into picture. So without theory, it will come down to some identity. So see, but anyway, you are saying that there is this matrix is equal to this, right?
Hmm.
Okay. But what does it mean? I mean, isn't it just a collection of equations, right? Why is it a collection of equations? Because if you look at the ith row and you look at the jth column, multiply these two. Or maybe I should not say ith row, jth column. I will say rth row and cth column for certain reasons, right? So what is the rth row, product of rth row and cth column? By your guess of this matrix and the definition of this matrix. What is it? So let's first write it properly. It is this thing and rth row. So okay. Let me again use some notation. We're running over S. We are running over S, and here we are obviously running over S, and this is C. S is going from 1 to 10. Fine. This thing, what will you say about this thing? This thing will be 1 if R is equal to C and 0 otherwise. Right? If this product has to be equal to this matrix, identity matrix, then it should happen, right? The rth row times the cth column should be equal to 0 if R is not equal to C. And if R is equal to C, it should be equal to 1.
See,
You
there
agree?
is 1.
Yeah. So I'm just using the definition and nothing else, right? Just the definition of product of two matrices being equal to identity. So this thing we say delta RC, Kronecker delta function. I mean, if you don't want to write it, then you have to write some words, right? It is equal to 1 if R is not equal to C, R is equal to C, 0 otherwise. And if you don't want to write it, then it is just that. Okay.
Just like the discrete.
Yeah, discrete. Yeah, you can think of. It's just a function which, anyway, that is not very important. But what is important here is that this thing, this thing comes out like this, right? So what is this? What is Pn comma n sc? That you know that the SCth entry is S choose C. No, sorry, I have written things wrong a little bit. I think. Have I written it?
Actually, I'm not getting the term S choose C. The
You
I
are,
choose J.
yes, yes, you're getting it right. Yeah, correct. So
No, I'm
yeah,
not getting actually the term.
okay. You're not getting. Let me see the writings. No, no, no. You're correct, right? I mean, look, if you look at the rth row of this thing, so look at this thing. Yeah. If you look at this thing, then what is your guess? Your guess is that the rth row, sth column is equal to r plus s, r choose s. Right? Because
Plus
that is
S
what
is okay.
it is okay because that is what P was, right? Yeah, and you told me that it is same as P, only sign is changed. And sign is changed like this only, that you have to check. Right?
Now I'm just asking about the R choose C. That what that means actually.
Oh, okay. R choose C is this. R choose S. Like this. Choose. Binomial choose. Okay,
Okay.
okay. That is the
Okay.
standard notation. Yeah, yeah. So in Indian books, usually they write C, but no, no. Nowadays, I think they write. Anyways, that's
No, no, we also write this, but you are
uh,
telling in
okay,
as you
okay.
choose. And I'm
Because it's
confused.
choose, right? What else is it? That is the thing. That is what it is. Anyways, and then this is S choose
Okay.
C, S binomial C, whatever, S combination C. It is this, right?
Hmm.
And you have to prove that this is equal to 1 if R is equal to S, which is very, very easy.
And
Please do it. This is very easy. If R is equal to S, then this is 1 is very, because most of the terms will be 0 actually, because C will become bigger than S and so on. Okay. But you have to show that it is 0 if R is not equal to S. And this is a binomial identity. Maybe slightly more difficult than standard JE problem, but maybe JE advanced level, you would have done this. Okay, so it is comes down to that. Okay, it is an identity.
one.
Think about means write it and try to prove it later. Yeah, yeah.
Okay.
You have seen these identities, right? This kind of identities. A lot of things were there, right, when you were practicing high school. So it is one of those. Yeah. Think about it. This maybe we will not prove because I will leave this with some extra problem solving sessions later on. We will. Okay. So I think, yeah, then let us stop here. Okay. So there is a lot of work. You have to collect them and do them. And after you do this, then move back to R10 and try to proceed with the later problems. Okay. And if you have any doubts, you can just ask, send me a mail or something.
Okay, I was asking about the diagram last time.
Oh, yes. Okay. So let's do the diagram also. Yeah. All right. So the
And
diagram.
one more thing, one more thing. Yeah, just show me the answer script which I have sent you when you were writing on the first page.
In the first, you mean in the mail?
You are correcting my answers there.
Oh, yes, yes. But I
My
think it
answer
is,
script that I
uh-huh.
sent you.
But I think it will be, means that correction will be gone. It is, I was just writing on it. That is not saved. Sorry.
Here, yeah, to third line, you used greater than equal, but isn't it less than equal? The
Which one?
previous page.
Previous page. Okay.
The previous page.
This one? This page?
Yeah, yeah.
Okay.
Hmm.
All right. Sorry. Where?
Down. Yeah.
Mm-hmm.
The second to third line.
Yeah, it will be greater than.
So in this third line, we have some more.
Oh, sorry. Uh, oh, okay, okay. So that is your, okay, okay. That's what you're saying, right? Hmm. All right. Yeah. So I see
Yeah, yeah.
something,
Now it's
yeah, yeah, right. So something I said was wrong. But then this also should be wrong because we gave a counter example, right?
Yeah, that's another.
but yeah, that's right. But we should say it is wrong from here only. Yeah. Um, okay. Right. So if here you are taking the ith row and then you are multiplying, and then that you will multiply. Okay, right. So then this one has more terms. Correct. Yeah, I think you are right. Okay, let me look at it. I mean, somewhere it is wrong, but we will see it. Okay, I will look at it.
Oh,
Right. But we know that it is not correct, but yeah, I mean, we have given it a said it in an indirect way. But yeah, that particular comment was wrong. Right. Let us look at this diagram. Right. So you see, suppose that this is 1,0, okay, and suppose that this is 0,1. Right. So these are the two inputs. Okay. Then what the diagram is, maybe something like this. Yeah, this 1,0 is not a good thing. Maybe it is small, right? Okay. So this is the two inputs, and let's take this output. So how much is this? Maybe 3,1, right? And let's take another output, right? Maybe so 1,3.
mm.
Okay, something like this. So what does this say? It means that there is a matrix which is sending 1,0 to 3,1. Okay, and it is sending 0,1 to 1,3. Right.
Okay.
And what kind of matrix will do it? I mean, at this point, you can guess if you have not still done going from matrices to linear transformations, but it's quite an easy guess. It is this matrix. It's not just a guess, you can understand. So this matrix may you can see put 1,0 and this is the output. The whole point is that
Oh, yeah.
right, these are the inputs and these are the outputs,
Mm.
the output vectors. Okay, and
Mm.
the the thing about linear transformations is that if you take if you now take the sum of, suppose you take the sum of these two vectors, then these two input vectors, that's the good thing maybe about linear transformations, that if you take the sum of these two vectors, then you come here, for example, right?
Yeah.
I mean, maybe I should not draw these extra things, not needed. Sum of these two vectors is here, right? What will be the
Mm.
output of
Mm.
this? So the output of the sum of the inputs is equal to the sum of the outputs of the inputs, will be this.
Can you repeat the last line?
Yes. So whether you take sum first and output later, or output first and sum later, it doesn't make a difference, right? So what I'm saying is that you take this input and you add those inputs and you try to see what is the output of this input that you can check in the matrix. Okay, I am claiming that it will be this point. And why is it special? Because this point is the sum of the outputs.
Okay. Okay. Okay.
Yeah,
Okay. Okay. Got it.
understand? And that is
Yeah.
not anything special. I'm just saying that if you take two vectors and sum the inputs and then take the output, that is the same thing as take
Or
the outputs, yeah,
say AU. Yes. Yes.
and
Mm.
add the outputs. That's what I'm saying. It's nothing. Just that is all this diagram
Got
is
it.
saying. These diagrams are very important. They will tell you what can be true and so on. Okay. So let's stop here. We will
Mm.
meet on
Yeah. Yeah.
Tuesday at 30. Okay. All right.
Okay.
Thank you.
Okay.
Keep doing your work. And
Okay.
yeah. All right. Bye.
Good night.